Our first speaker today is Sergio Marchese from OneSpin Solutions, where he's the technical marketing manager. His talk today is on AI chips and must get the math right. Sergio Marchese is, as I said, technical marketing manager at OneSpin Solutions. He has 20 years experience in the electronic chip design business and deployment of advanced hardware development solutions across Europe, North America, and Asia. His expertise covers IC design, functional verification, safety standards including ISO 26262 and DO 254, and detection of hardware trojans and security vulnerabilities. He is passionate about the enabling the next generation of high-integrity chips that underpin the Internet of Things, 5G, artificial intelligence, and autonomous vehicles. So over to you. Thank you, Sergio.
Thank you, Mike. Thank you also, Sarah, and the whole team to organize this event. It's nice to be able to still, keep kind of a normal working life in these times. So I'm going to talk about arithmetic into AI chips, and in particular, floating point arithmetic. And so this is let's say one specific aspects of this type of silicon, but very, very important. And also we'll see some numbers that demonstrate this support this statement. So OneSpin provides IC integrity verification solution to develop functionally correct, safe, secure and trusted integrated circuits. Functional correctness is about ensuring that the hardware does what it's supposed to do. Safety is about providing evidence that silicon meets certain safety standard that is tolerant to random faults into the field. And trust and security is really a lot about assuring that the hardware does not do anything that it's not supposed to do. And the specific talk, really, the focus is on functional correctness and specifically on data path side. So if you are lucky enough to have Tesla, you wanna at least one of the newer ones, and you wanna go under the dashboard, you probably should find the box like this, and then inside that there should be a board which has two quite big chips in it. And if we look into the details on these chips, which are called full self driving chips, the Tesla made quite a lot of presentation and released a lot of information on this chip about a year ago. It's a 14 nanometer CMOS technology. It has like 6 billion transistors and 260 square millimeter area. And if we, obviously there are several subsystems here. I like to draw attention on this section 8 here. And this is really the neural network accelerator. So there are two instances of this, 1 and 2. I hope you guys see my pointer. And so as you can see, this for a start, it takes a lot of area in the chip, these neural network accelerators. Apparently they consume in the board 15 watts of power out of 72 for the whole autopilot software stack. And Tesla claims they can process 2300 frames per second coming from all the cameras that the car has. So you can see already how this portion of the chip takes a significant portion of the area. It's actually quite the biggest part in the chip, and also power. So if we look at how this hardware helps into, for example, vision algorithms, we know that a lot of software use convolutional neural networks algorithms, which here we have kind of an example taken from a paper where you have a lot of nested loops, and then ultimately you have multiplication and addition. And if you look at this again from Tesla, these numbers here, you can see that 99.7% of the operation done by the neural network accelerator is really good old multiplication and addition. So you can see how critical actually these basic operations are, and they really take a lot of the power, a lot of the area. In the specific case of Tesla, which obviously is a kind of an extreme vertical integration, one chip for one very specific product, they can get away with integer arithmetic to, you know, save power. But in most chips, you will find that you have a floating point hardware. Although quite often, you know, you don't need like double bit precisions, but sometimes even 8-bit precision, often 32-bit single precision is sufficient for this type of applications, like, you know, image classification and object recognition. Another example here, obviously, we have Xilinx AI, Versal AI core. You can find more information, obviously, in the Xilinx website. This is quite different from the Tesla example, because this is obviously targeting a much wider range of application. It's not just for one specific product, of course. And here again, you have a large array of AI engines which support floating point operations. So one of the advantages of floating point arithmetic compared to fixed point is that you can cover a wider range of values without losing precision. Here in this picture, we see how the encoding looks like for floating point operand complying with the IEEE 754 standard. You know, you have a sign bit, exponent, and mantis, and then this, you know, the width depend on which precision you use, half, single, double precision. The drawback of using this type of arithmetic is that one of the drawbacks is that the hardware is more complex. And of course, this complexity also implies some verification challenges. So the verification of arithmetic, and in this specific instance, we are talking about FP arithmetics, is obviously crucial in AI engines, although I would say it's crucial in a lot of other applications as well. But we have seen how in this type of application it really takes a lot of power and area budget, this logic, so you want to make sure you get it right. And actually, even a small bug can be devastating, because when you accumulate a small error over many operations, you can end up with a huge error, actually. And I mean, you cannot talk about verification of floating point arithmetic without reminding, you know, the people of the Intel FPU bug in the mid-90s, which apparently costed Intel $500 million. So what are the challenges in FPU verification? Well, for a start, you know, the standard itself is quite complex. There are many operations defined by the standard, not only arithmetic, but also, you know, comparison operation, type conversions. It supports multiple precisions. There are actually 5 rounding modes and 5 exception flags. And there are lots of special cases. The normal, not the number, plus minus infinite, plus minus 0. Can be strange to see, you know, you actually get the sign to the 0, but this is one of the scenarios, for example, where we found bugs, where our customers found bugs with using formal verification, because, you know, it depends whether you do plus 0, minus 0, the results that you get might be different. So verification is often incomplete and time consuming. I mean, if you use simulation, you have, you know, you probably going to need significant time to set up the test and generate the stimuli, coverage, and then, you know, you're still not going to hit all corner cases, particularly if you have corner cases that depend on implementation details that you don't know. It's quite likely that you're going to miss them. Another approach could be, sequential equivalent checking of your RTL versus like a reference model, like high-level C++ System C model. But of course, one of the drawback here is that first of all, you need this additional model, and then you quite likely are going to need to have, some implementation detailed knowledge of the two models to actually carry out the verification. And then, if you use formal with assertion, of course, you need again expertise and time to write the right assertions. And you might also incur into inconclusive proofs, and then maybe you need to do additional effort to, to get to full proofs. This, of course, quite often requires some expertise in formal and also in this specific type of problem. So at OneSpin, we have come up with an app dedicated to FPU verification. And one of the goals is to really accelerate the verification. So this is not only to try to prove full correctness of your hardware, but actually immediately deploy the app during the RTL development and check right away without the need to develop a test bench, whatever functionality you have implemented up to that point. The app reads, the RTL implementation of the FPU. You can configure it, for example, design the precision, which rounding mode, and you can also customize it because sometimes we've seen at least at one customer that they needed to encode some intended deviation from the standard, the IEEE 754 standard. And inside the app, what you get is, under the hood, you get, first of all, proof optimization dedicated to the specific type of problems. You get, this is quite crucial, the SVA model of the IEEE 754 standard. So you don't need to be an expert in the standard and be careful with all these strange corner cases. It's all already done for you. You also get coverage metrics, functional coverage, and also mutation type coverage, and also some debug features to speed up the debugging of failing assertion for this type of specific problem. The app is very easy to set up. It supports, half, single, double precision, also bfloat 16, which is quite popular in AI application. And also you can define custom precisions. It supports all the rounding modes and the exception flags. Many of the operation, add, sub, mul, FMA, and so on, and also conversion and comparison operations. It also provides parameters to specify what behavior you want in the situation where the standard is ambiguous. So this situation already captured for you, so that you don't forget about them and you make a conscious decision how you want your hardware to behave in these specific cases. We also have a predefined configuration to have your hardware compliant with the RISC-V standard. And of course, you don't need here any additional model, any C++ model, because you already have a model inside the app. And as I said, you can implement the intended deviation from the standard. So the app has been used by our customer in a range of different applications, in chips for AI platform, also automotive core chips, and also have been applied to open source RISC-V cores and also open source floating point intellectual properties. And in all the applications, it has found bugs. And also, quite crucially, the effort necessary to carry out the verification was really, in the order of days compared to weeks or months, even with simulations. So in this specific case, we had Xilinx deploying this app, which is now part of the flow. Their design was compliant, mostly compliant with the IEEE 754 standard, but had some few minor intended deviations. It was supporting single precision. And in particular, they focus on addition, subtraction, multiplication operations. They had already actually verified their IP with simulation and emulation. So what they did also to gain confidence and test the app was to run it on previous version of the RTL with known bugs. And the results they obtained were quite good. So first of all, they detected all known bugs, and they also detected one additional issues. And they, of course, in this scenario, they could compare exactly the effort they had to throw into this task in simulation and informal, and they reported a reduction in the verification effort of 5x. And this is also including the effort they had to put in to ramp up with the tool and with the specific app. So that's even including this kind of ramp up effort. They got a huge verification effort reduction. And for this specific instance, the tool was also able to achieve full proofs. And these are the proof times, and particularly for the multiplication, this is actually quite impressive results. I mean, if you are familiar with formula, you might know that this type of proofs are not the formula's best friend, really. But with this app, they were able to quickly achieve full proof. So in summary, we have seen that arithmetic and in particular floating point operation are crucial in many applications and a lot into AI applications. We've seen how much area and power goes for this operation, so it's really crucial to get them right. I've seen the one-spin app, how it can reduce verification effort from months to days. It includes, a model of the standard. And I think one of the things I want to stress is really this app is not only to prove correctness, but really to deploy immediately and check your design during RTL development. Last thing, there's a quote here from Xilinx engineer about their experience using the app. And I want to highlight that, the work they did not require using any abstraction or any assumed guarantee partition. They just deployed the app into their project, and the results they got were like out of the box. That's it from me. Hope you enjoyed the presentation, and do you have any questions?
Thank you, Sergio. Mike will go through the questions for you. Mike, are you still with us?
Oh, yeah. Yeah, sorry. Yeah, I was with you. I just needed to unmute. Sorry.
I always forget that as well.
I was talking, but nobody was listening to me. So that's usual. Yeah, so there's one question regarding accuracy, because that came online. I think at the beginning of your presentation, Sergio, you mentioned that sometimes these applications do not always need to have 100% accuracy in order to do video analysis or vision analysis. Can you talk a bit about lack of accuracy and how that will affect the verification?
So, I mean, I'm not an expert of convolutional neural networks. The point is, of course, that here you're using a lot of area and budget and power. So you want to use the hardware that you need and no more. So apparently for this type of algorithms, you get sufficiently accurate results with this type of precision, like I think some chips also have up, down to half precision, like 8-bit operands. So I mean, once you set, let's say, the requirements from the algorithms, and you set the precision you want to use, and you want to try to use as little as possible for power and area reason, then you still have your verification problem left, And of course, especially if you use formal and you use lower precision, that obviously helps in terms of achieving, fast proof and full proofs. Of course, it's much easier to achieve full proofs if you're using 8-bit precision, half precision. So you have small operands. When in comparison, if you would use, for example, double precision 64-bit operands, the complexity of the proofs. In general, the verification, the same, even applies to simulation, I would say, because you need to look more corner case. So the verification gets more complicated.
Okay, thank you. There's another question that also relates to automotive, because as you indicated with the first example, it's an it's an automotive chip. So here, do the verification coverage numbers which you generate allow you to claim ASIL-D compliance?
So first of all, this example of the Tesla is using integer arithmetic, and I want to clarify that Tesla is not the one-spin customer, so I don't know how they have verified their specific, hardware. And regarding, the achievement of safety compliance, actually, I don't know how they have done it. I mean, in general, when you do safety compliance for an automotive chip, in any case, it's a bigger and high-level problem that the specific arithmetic verification. Of course, when you go into fault metrics and things like that, this type of arithmetic hardware also comes into play, definitely. But for this kind of application, actually, one-spin is a separate type of apps and solutions which help in computing the safety metrics for ISO 26262 compliance.
Okay, there's quite a few questions coming in, so I'm going to keep going. So how does the performance of your tool would say compare to another tool that just uses equivalence checking against a floating point IP library, for example?
So, I mean, the comparison really, it depends if you are comparing runtime or if you also compare effort, because the beauty of this solution is that, you can deploy it immediately with extremely low effort and find bugs immediately. Because formal is very good into finding fails. When you want to go to a full proof, then in the case I showed, actually I achieved full proof quite quickly. In other cases, especially, for example, if you go to double precision, you may not achieve full proof, and then you need to put, additional effort to get to the full proof. So what you typically have with the comparison with this high-level model is that you may have a quick runtime, but before you get there, you need to do a lot of work to set up your proofs. So, that's the difference, I think.
What, in terms of matching and that type of thing? Yeah.
Yeah, I mean, and also, kind of splitting in a sense, doing some sort of divide and conquer, kind of doing intermediate proof steps and things like that.
Okay, thank you. That's helpful. So another good question here: can you write checks on accuracy as well to check that the output, for example, is within NULPs?
I mean, you can write additional checks, of course, on top of what you already get from the app. So what you get from the app is compliance with the standard. So for example, if you prove the multiplication operation for a specific rounding mode that you choose, you can fully prove that for any input operands, that's obviously the beauty of formal, you will get the correct result according to the standard, the correct exception flags being flagged, and all these things. So the app ensures that your hardware is precisely compliant with the 754 standard. Then you can write additional checks if you want, and you can also write some additional function if you have some deviation from the standard that you want to implement, because sometimes that's also the case.
Okay. And just a final question along the same lines, really. I guess the question is framed. It says, how do you know you'll find all the FPU bugs? But I guess a similar question to that is, how do you know you've got full compliance? How do you know you found all the bugs and got full compliance?
So first of all, the app has been checked against many different models and customers, open source, FPU IPs, and RISC-V. So obviously, firstly, you get the confidence that this is something that is used across many different projects. It's also been developed by an expert in the standard. And there are also coverage metrics. And then, I mean, in terms of covering corner case, like operand-based corner case, that's really inherent in using the formal approach.
Yes.
That will inherently check for all possible combination of input operands.
Brilliant. Okay. Well, thanks, Sergio. It's a very good start to the conference today. So thank you very much, Sergio.
Thank you.